Okay. Okay. So I as usual, the last speaker before lunch shouldn't be too obnoxious and ruin guests' appetite. So I will just be brief, and my talk will be mostly conceptual. So I just hope to throw some ideas there that can be then picked up during lunchtime. So okay, so this is the outline of what I would like to tell you about. So first of all, I will just get into the main topic of today's session, which is divisibility, just to give me the pretext and to step further from that and move into something that it looks like divisibility, and it is actually related with divisibility. It is like other forms of divisibility, in particular, something that is related with the problem of initial correlations between system and environment, which is a problem that has been discussed in open system dynamics. And then also like a notion of divisibility, or the relation between a notion of divisibility and entropy production, again, in open system dynamics. Okay, so this is conventional divisibility, about which this morning Darius so nicely told us about. So the idea is that you have a system Q interacting with that environment, but it interacting in such a way that actually you can always think of it as interacting with some new, fresh piece of environment at each time, some kind of a collisional motive. So then the idea is that this conventional divisibility tells you that the system state at time ti can be predicted or inferred. So when we have a channel, it's nothing that really happens, right? Typically, it's an expectation that we do about the output of the channel. So the system state at time ti can be inferred from that at time ti minus 1. So essentially, divisibility is a condition of inferential locality, so that everything that we need, the information that we need in order to infer the next step of the evolution, is there ready for us to use, localized in the system. Okay, so this is the conventional divisibility of a process, well, or of a channel. This is like the core mathematical problem there. So I give you two channels with the same input, and now the question is whether there exists another channel, F, that connects the two, that is able to propagate the output of one into the output of the second, right? So it's formulated as such. It is a problem of statistical comparison, and well, I don't think I will go very much into this detail, into this topic, because I would like to tell you something new. But anyway, the idea is that you can always introduce some kind, look at this problem as a problem of characterization of a preorder. So I give you two channels, and the question is whether one majorizes the other one in terms of a post-processing channel F that you can apply on the output. And usually when you have these kind of questions, it is nice to have a bunch of what I call reverse data processing theorem, because the idea is that if you have such a relation between two channels, of course, the second one will be more noisy than the other one, right? So if this is the situation that you have at hand, data processing inequalities withhold, but now you want also to have some kind of reverse implication. So can we say that if data processing inequalities always holds, then can you find a channel that does the trick? So this is the content of these reverse data processing theorems, or what I also call like Blackwell type theorems, because these are all very closely related with the theory of statistical comparison and the Blackwell-Sherman-Stein theorem in statistics. Okay, so for example, an example of this approach was what we've done with Nilanjan in our paper, in which we characterize divisibility in terms of a family of monotones that we identified in guessing probabilities of some ensembles that propagate along the process, and then you check the guessing probabilities. If this guessing probability never increases along the evolution, and it does it so completely, so you also have to, of course, extend your system if you're interested about a completely positive channel here. This is equivalent to divisibility. But I would like, to step a little bit aside from this, main road to divisibility, because I would like to discuss some other problems. In particular, the first one can also be introduced starting from the idea of divisibility, but now, instead of having some kind of fixed process at hand, so with an interaction that is given to me by the physical arrangement, now my question is kind of stronger in a sense, or complementary, if you like. So now I would like to say, when does inferential locality hold for all subsequent evolutions? So say that I have some kind of joint system environment evolution, and then I freeze at some point the evolution. And then I ask, okay, the two systems will be correlated, but can I still say that there exists a reduced dynamics here, even in the presence of initial correlations for any joint evolution of the system and the environment? So now this is a property of the set of the system environment states that emerge from the first interaction, right? So it's not a property anymore of the process of the evolution, but it's a property of these correlated system environments. So if you want to formalize this problem in a mathematically clear way, so you start from a datum, from an initial condition. So I give you a set of possible system environment states. Okay, this can be as general as you like, even though, if you want to do a little bit of, if you want to derive some conditions, then you have to assume some assumptions, to have some assumptions on this set. But anyway, it can be completely general, right? And then the problem is the following. So the problem is to find conditions on this set of correlated system environment states such that for any isometric evolution, joint evolution of system and environment, there exists a corresponding CPTP linear map on the reduced system alone, such that you have a kind of commutative diagram here. So taking any state in the family, taking the joint evolution and then tracing over the environment is like tracing before the environment and then applying the CPTP linear map. So when the property above holds, we say that the set is CPTP reducible. So this is the diagram I mentioned before. So the setup is the line on the top, right? So you start with states that belong to a set of initially correlated system environment states, and you evolve these states with some isometric evolution V. And now you can take the partial traces at the beginning and at the end, and you want to see whether these local states are compatible via a CPTP linear map that depends only on V.
Did you say initially correlated?
Correlated, yes. And this is a problem because you see that in order to construct this green arrow, you would like to go the other way around, right? You would like to go from rho Q to rho QE, then evolve with an isometry and then partial trace again. So if you could go back, then by composing these three arrows, that would be all CPTP, you will have constructed your CPTP linear map here, but the arrows go downwards, right? So is there a way to attack this problem? So how to characterize reduced dynamics of a system that is initially correlated with its environment? So the idea, of course, is to start by assuming that there exists an arrow that goes up. Okay, so this is the approach that was taken in this quite influential PRL, followed by a comment, PRL that was written by Pichlukas in 1994 and then commented by Alitsky. So there, the idea is that you essentially assume from the beginning the existence of an assignment map. Okay? So some map that takes states here. These will be states that belong to the reduced set here. So you just partial trace over the environment and you're left with a bunch of states on Q. And you assume that there exists a map that is able essentially to lift this rho Q into a correlated state there. And then you can assume that this assignment map satisfies some natural properties such as linearity or positivity, or if you like, complete positivity, or in particular consistency, right? So we would like that if you go up, you lift your state and then you come back onto your system, you are consistent, right? So that you end up where you started from. But this condition about the existence of an assignment map is very restrictive. So in particular, it's essential, you know, saying that the solution to the problem was there from the beginning, right? But typically that's not what happens, right? Typically you can have families for which there exists no such an assignment map. For example, a simple initial condition like this one. So it's like the opposite of what typically happens in textbook presentation of open quantum system dynamics, where here you have a fixed state of the system and many possible different states for the environment. So such a situation that, you know, you can think of, so it's not so weird, but this situation would fall under the condition of an assignment map, just because, you know, you have a single state that corresponds to many different extended states. So is there a way in which we can try to give us a little bit of slackness and try to say something a little bit less straightforward than what is done here? So the proposal here is to replace the notion of existence of an assignment map with the notion of preparability. And also, like, it's kind of reasonable, because how can you say that you are given a set of states, initial correlated states, if those states are not prepared, right? So what is the notion of preparability? Preparability says that there should exist some system X on which you don't have many assumptions. Okay, it can be highly dimensional, lower dimensional, whatever you like. And a completely positive map, but not necessarily trace preserving. So kind of filtering operation that is able to output with non-zero probability any state in your set, okay? So upon inputting some state of the input system here, then your filtering operation will click or will not click, but if it will click, it will output some state in your set. Okay. So the interesting thing here is that the preparation that takes some input state rho x into a state in your correlated family of states is completely positive by definition, but is not necessarily linear nor consistent. It's non-linear because here you're normalizing by the trace, right? So it's quite general. I mean, you can actually play a lot with these objects and still consider the question of characterizing the complete positivity of a reduced systems dynamic. So in particular, all families of states which are polytopes are preparable. And the idea is very simple. Just you take a classical X. So each classical state of X will correspond to the vertices of the polytope here. And that's how you prepare the entire polytope. So then what is the operational meaning of preparability? So you can imagine that is something happening like that. So the set of correlated states in the family that you are considering is preparable whenever there exists a physical process, which is this big blue box here, such that at each use, it says yes or no. Okay. If process says no, discard and repeat. But if process says yes, then you know that a state in SQE was emitted, and any state has a non-zero probability of being emitted. So it's really like a physical way in which you can prepare this family of initially correlated system environment states. And I would even argue that if your family SQE is not preparable, then it doesn't make much sense to consider that as an initial starting point.
Do you require X to be classical?
Yes, sure, anything.
But is it required to be classical?
Oh, no. In general, typically, if it's not a polytope, then you need, some places where you have curvature, and that's done with a quantum.
And are there non-preparable sets?
Yes, I think so. They could be weird, for example. Well, now I will give you an equivalent representation of preparable set, and we will see, very easy to understand actually, and we will see what kind of things you have. I don't have a complete characterization, but I think one can cook up some weird object that is not prepared. Okay, preparability is equivalent to steerability. So a set of states is preparable if and only if it is steerable. So if and only if you can introduce a third system, a reference system, and a tripartite density operator, such that any state in your family can be steered from omega RQE by some effects, measuring something on R. Okay, so essentially, the idea of characterizing the steerable sets boils down to the problem of characterizing this steerable ellipsoid. I think there is literature about that, but it's a difficult problem apparently. So there are only like partial solutions to it.
It's related to cones,
Definitely so, yes.
because if you ignore the normalization, you're looking at certain cones.
Yes, and you want to see the intersection of this cone with some state space that you start with. So the example I showed you before of this silly family of states where the state of the system is fixed and it is the state of the environment, the one that changes, cannot be treated under these assignment map formalism, but it can be steered. Sorry. How do? You just take a maximally entangled state between the reference and the environment, and then you fix this guy here. So having a maximally entangled state means that you can steer anything that you like on the environment. For example.
Sorry, can you go back to the definition of preparability? Well, so what's wrong with taking X equal QE and then say epsilon equal the map equal to the identity?
It would be kind of a recursive. Like I want to impose some structure on this SQE that allows me to derive some theorem.
Yeah, sure, a bit, but just if you I don't know if X is
Oh, this has to be. Oh, okay. Well, the idea is that this guy can be any state here. So you want that you just input the whole state space of something. So if SQE is very weird, it might not be convex, for example.
So
It might be some sparse points here and there, or have some strange shape. So here, anything that you input.
definition compiling for like for X equals QE, I think you get everything. But okay. Yeah.
This is the whole state space of X.
Yeah, but you're just saying for any row that exists row X. So I take row X equal to row QE.
Okay. Oh, yeah. I think so. Anything that you input will get out something in there. That should be probably the right definition.
So then you should, okay.
For any instead of there exists.
It is subject.
it's both.
You
For
want
anyone
like
you
a-
want,
Yeah,
there's this
exactly.
one, but for everyone you set inside.
Yes,
So
and
the
image
second
just
one
the-
is
anything that you input will output something in there.
images of
You have
unit.
to think about a kind of filtering thing, so that you enter with anything, so you don't control.
No,
the
sure,
input,
sure.
And then you are sure that if the filter clicks, it outputs something on SQE. Yes. Thank you very much. This is very good. Yes. Okay, but in terms of steerability, it is much clearer, right? I mean, you want to be able to steer your family. Okay, and then what you can say? Then you can say something that apparently is very simple, but it simplifies a lot of literature that was out there, and it was very hard to even to vet whether it was correct or not. So then you can conclude that your set SQE, if this is preparable and CPT reducible, it is equivalent to say that it can be steered from a Markov state, a Markov triplet. where the Markovianity condition here is that given Q, R and E are independent. And these things can be made like robust against epsilon deviations because, the Markovianity condition can be is robust, right? You have the theory of approximate recoverability that helps you with that. So, so here you have Markov property, which is again a property of inferential locality. Okay, and the above proposition tells you conditions which, if satisfied, guarantee that the system can be localized in an inferential sense, even if it is correlated with its surrounding environment. And then there are some examples of these. So of course, the trivial example, the example where you don't have any correlation, it can be seen in this formalism where your tripartite state is just the maximal entangled state, and then you tensor some fixed state of the environment. And then of course, this state satisfies the Markovianity condition. So it is CPTP reducible, right? So the paper that I mentioned before by Pichukas was arguing the importance of going beyond the factorization assumption, and thus the importance of considering non-CPTP reduced dynamics. But it's missing the point, in my opinion, because in general, you don't even have a map. So it's not the problem of saying whether the map exists and it is CPTP. Sometimes you just don't have a map. So the problem that one should be interested in is, can CPTP reduced dynamics arise also with initial system environment correlations? And well, the answer is yes. And this was known since a long time. In particular, there was this paper by Rodriguez Rosario and collaborators, where they show a construction of correlated states that give rise to a CPTP dynamics. And their proof was kind of having calculations because they were constructing the dynamical matrix, which is a kind of joy operator, if you like, or kind of Minkowski operator, and then you check conditions for positivity there explicitly. So their counterexamples was like this: you fix n environment states, and then your family with this will be this polytope, right? So you have orthogonal flags on Q, and then these states on the environment, and what you change is just the probability distribution here. Okay. And they prove that it is these kind of families give rise to a reduced CPTP dynamics on the system, but it can be proved very quickly also with this trick of the Markovian tripartite state, just by choosing, for example, as a tripartite state this guy. And then you see that because this is orthogonal together with R, it is Markovian. Given Q, R and E are right, and therefore it is CPTP reducible. But then the question was, are there other possibilities? Because this set was, kind of the marketing behind this set was that this set is a set of zero discord, like correlated states that have zero discord. They are classically quantum states, CQ states, okay? So the question is, can you have things that are not CQ states? And there was a very influential PRL paper by Shabani and Lidar in 2009, claiming that that was the end of the story, that the only correlated states that give rise to reduced CPTP dynamics are those with zero discord, because discord was a big thing back then. And so, of course, they wanted to say that, oh, discord is useful. And actually, this was, one of the crown jewels of this thing about discord, right? But no. Unfortunately, because there is again another counterexample that again was constructed by these guys, and again can be very easily understood in our formalism. Again, there the calculations are explicitly and hard to bet. I would like to invite you to have to take a look at the paper by Shabani and Lidar.
Can I just interrupt and say it's a different data?
yeah. It's Animesh. So their construction was as follows. You have just three distinct states of the environment. You choose them as you like. They just need to be different from each other, not the same state. And then you use those three to construct these two states that are correlated. And you see that because Q here has a 0 and a plus is 0 plus 1, okay, in this sense, this state in general is not CQ. Okay, so this state is not at zero discord. But again, if your family is like this, so if your family is just a polytope where you can prepare this state alpha with probability p and beta with probability 1 minus p, and you can choose p as you like. This is a set of initially correlated states that gives rise to CP, PP reduced dynamics. And in our formalism, the proof is straightforward just because you see that this is non-zero discord, but still these are orthogonal, right? The Q here only works on the subset 0, 1, and here Q is on 2. And so you can just imagine to prepare your states in this way. And again, is CPTP reducible. If I give you Q, only Q, you partial trace over E, I give you Q. Q is distinguishable, and I can prepare alpha and beta. So it's Markovian, and therefore it's CPTP reducible. Oh, actually, they are even, even in the face of a counterexample, they're still claiming that their paper is correct. It's correct when it's correct. Like it's funny thing like that. Under certain assumptions, we are right. It's a weird situation. But anyway, so then the thing is, do you have more? You have more than these examples. Okay. So can we have CPTP reducible sets containing entangled states? Because until now I showed you just separable states. Of course, like the whole point is not about the strength of this correlation between system and environment, but the point is about this family of states, how this family will construct. Right? So the core is this Markovianity condition here, and of course you can play around and you can have very entangled states between system and environment. The point is that there will be a kind of non-trivial interplay between the correlations between system and environment, and somehow the volume, right? The relative volume of this set of states SQE with respect to the whole ball of states. But the point is Markovianity. It's not something about the correlations themselves. So, but there is a funny corollary that if you require that your initial set of states SQE is so that by throwing away environment, you reconstruct the whole set of density matrices on Q, then the factorization condition is the only one that works. So somehow, you really have to have you have a CPTP dynamics, but the family of states it's working on is contained, strictly contained in the whole set of density matrices. But you can. Okay, so now let me quickly go to another conceptual topic, I would say, that is the role of inferential locality in entropy production in statistical thermodynamics, stochastic thermodynamics. So this is how entropy production is typically introduced. So you consider in classical stochastic thermodynamics. So you consider a stochastic system, a stochastic evolution of a system that have some possible set of initial states X and some possible and a set of possible final states Y. And you say that there is a forward process. So some kind of joint distribution on X and Y that just tells you that, what is the probability that the system starts in state X and ends up in state Y. And then you will also have a reverse process, which is again a joint distribution. I just flip these two labels just because, just to remind that now it goes the other way around. So it's considered something that starts in state Y and ends up in state X. And the stochastic entropy production there is defined as the logarithm of this ratio. And this is the typical assumption there. And of course, the freedom there is that you can define the reverse process as you like. So as long as this is a well-defined probability distribution, all the formulas will go through. The fluctuation theorems, Crookes fluctuation theorem, Jarzynski equality, everything. So what does it mean? Like does it mean that why you call it reverse process if you can actually put there anything that you like? Is there something hiding there, right? Because then at the end of the day, entropy production is something that you use to measure the reversibility of the process. But there is a very important thing to notice, very simple, but very important. If we impose that the entropy production is local, in the sense that we impose that this log ratio of the forward and the reverse process can be written as the difference of two functions, okay? I don't even ask that it's the same function. I'm just saying that one is function of y and the other one is function of x. And it is typically the situations where formulas work out nicely. Know that you can write entropy production as delta something, delta entropy or something, like some differential of some point. If you impose that, then what you can do, okay, you take the exponential of both sides, you divide by the priors here, so they go in the same direction. So now you have a ratio here of two new functions, g tilde and f tilde. So just by rearranging thing you have there, then you sum over x, okay? And because this guy has to, so I'm forgetting about all problems that you might have with zeros. I'm taking all these things to be full support, okay? So I don't have to deal with zeros. But the point is that if you sum over x, this guy is going to give you 1 for all y, and so you have this, which means that the reverse process, whatever that is, so if you want the entropy production to be local, then the reverse process has to be some kind of Bayesian inverse of the forward. You cannot escape from this logic, okay? So a Bayes-like form for the reverse is equivalent to a locality requirement for the stochastic entropy production. And the Bayesian form of the reverse process, because I'm speaking in the section devoted to divisibility, I would like to argue that again is a divisibility condition in disguise. Why? Okay, so just look at what it could mean to say that you are constructing a reverse process, the reverse of an open evolution. So you might think about 3 constructions. Actually, these are the 3 that are there in the literature. So one possibility is that to say, okay, I do full Hamiltonian reversal, okay? I haven't the open quantum system dynamics, but I pretend that I actually have everything. I have the environment, I have the unitary. So what I do, I just apply UDAGA. I just apply the inverse unitary on both system and environment at the same time. Okay, this of course will bring me back exactly to the initial condition, but this is non-local and non-operational. Non-local because I'm not using only information that is in the system, which is the thing that I should use, right? Because here I'm working in open system evolution. So I only have the open system, right? By definition, I don't have access to the other degrees of freedom that might or might not exist actually, right? So this is, in a sense, it's something that one can think of, and people have been thinking of this way to construct the reverse process. But I would argue that it is not a good way to construct the reverse process of an open system evolution. Then you have the physicist's reverse. I say the physicist's reverse because it is very intuitive, right? What you do, okay, this works actually, it's a very interesting thing that this works for thermal operations. So this is actually what happens if you start from an environment which is in thermal equilibrium, and then you apply some unitary that could be, for example, energy preserving. Then if you want to do the reverse process, then what would you do? Oh, you say, oh, the bath is large, it doesn't change. So I just take another thermal state of the environment, but now I make the interaction to be so that UDAGA is implemented. So this would be local because I'm just using the non-trivial information that I use is on Q, but it's often unjustified. I mean, why on earth such a simple picture should work at all? So it is actually striking that in some situations, it is the right thing to do. But in general, okay, when you don't have any structure to rely upon, the thing that is local and operational is to construct your reverse according to some Bayes rule that can be generalized to Jeffrey probability kinematics, or in the quantum case to the Betz transpose map. Okay. And typically, when you have good formulas for entropy production, you always are here, even if people don't tell you and don't realize. So this is an example of these Bayes-Jeffrey Petz reverse in action. Okay, so suppose that you have a 2-point measurement process. So something like this. This is a kind of trivial thing. People have been using this in quantum thermodynamics to start saying that, oh, we do something quantum, but it's not really quantum because both input and output are just classical labels. But you can say that there is something quantum going on in there. So you have a forward process. Okay, the forward process is that you prepare some orthonormal basis here, which evolves with unitary and then is measured with the POVM here. So how would you apply this Bayes inverse, Bayes reverse on this process? Well, you need a prior. So say that you take a prior distribution to be the uniform one with respect to which you do the Bayesian inversion. You would end up with this thing here. Okay, so what is this? This is preparing these density matrices here, evolving them through the UDAGA evolution, and then measuring at the end the basis phi n. So you have something like this. And if you compute the entropy production, you end up with the difference between observational entropy, which is this quantity that also Andreas have been studying with Joe, Schindler, and von Neumann entropy. Yeah, I find it very, very, very pleasant from the formal viewpoint that the difference between these two quantities that are of independent interest here emerge very naturally from considering the reverse process of a kind of measurement procedure like this. So my final note that I hope will tickle a little bit your interest. So now, if any nice, in the sense that any local and operational definition of entropy production necessarily involves a reverse that is inferential. So it's not a physical reverse. We are not doing, it's not that you are turning knobs and pushing buttons so that your Hamiltonian becomes minus Hamiltonian or whatever, right? It is really an inferential process, a Bayesian process. Then, you know, when you're looking at an increase of entropy, what is there? It's not about irreversibility of the physics, whatever that is, but it's something about irretrodictability. And this is something that was brought up already many years ago by Satoshi Watanabe. So in my way to say this is that we can understand, in a sense, why the second law of thermodynamics is so special among the laws of physics. This is the famous statement of Eddington, no? Like, oh, you have a theory, if it violates Maxwell equations, it's fine, but if it violates the second law of thermodynamics, it can only be humiliated and fail in a miserable way. Why? Because if you look upon, you know, entropy production from this inferential viewpoint, then it seems to tell you that the second law is special precisely because it is not the law of physics, but it is a law of consistent reasoning about physics. So if you violate the second law, it's because you didn't reason in a consistent way. Somehow, you know, your logical inferences are astray, are odd. Okay, so these are some references. So concluding, so take-home messages. So divisibility, I would like to argue that divisibility is one avatar of a more general concept that could be called like inferential locality. That sometimes appears explicitly, like as it is in divisibility and Markovianity, sometimes less explicitly, like in separations between system and environment, or work and heat, or these kind of things. Sometimes really implicitly, so you really have to dig deep in order to find where this inferential locality appears, like in entropy production. And then, you know, that this inferential locality seems to be closely related to Bayesian inference. Bayesian inference, Bayes' rule, in a sense, is local, right? Because you can change the input distribution, for example, just by working on the x's alone, right? And that happens also with Jeffrey prediction formalism that only works on the y's. You don't have to work on the joint distributions. But then, there is the nice question about how would the proper formalism of fully quantum electrodiction, something that then would allow you to like fully quantum fluctuation relations, for example, and Choi operator gets close, but it's not the analog of classical Bayes formulas. So probably I don't know. We need some new idea. Look out of the box. Maybe abandon even the idea of positivity and have some fantasy and look around and think. Okay, and that's it.